She's actually visiting us from University of California, Irvine. She has a bachelor's degree in materials physics from University of Science and Technology of China. And then she came to US to do her PhD in material science from University of California, Davis. And she spent quite a bit of time at Davis, first as a PhD student, then as a postdoc. And just very recently, she moved to University of California, Irvine, actually in December. So
Yeah,
just maybe a couple of months. Partly because our advisor ended up moving to University of California, Irvine, so she ended up moving there. Welcome to CSU, and we're looking forward for your seminar.
Thank you. Thank you for the warm introduction. And it's been my great pleasure to be here and giving this seminar. Thank you all for coming here. So you see the title here, I'm going to talk about the nanostructuring of very complex engineering materials. That's more focused for my previous research. And I put the logo of Boeing and Office of Naval Research here because I would like to acknowledge them. They funded most of my past research here. So before I go into the details of this, since my background is material science and engineering, and I have been teaching a class of material science and engineering design, I would like to give you an idea of how I interpret the importance of material science and engineering design here. So as mechanical engineering, you're probably very familiar with the design process where you can come up with a concept according to the market needs, and you need to perform detailed embodiment and turn it into a real product. But while you're doing all of design process, you're making things, right? And you're making things out of materials. So which actually put the material science engineering integrated to the design process. Because you need to understand the whole world of the materials before you can choose a right materials for your product and a right appropriate process to make your product here. And to me, the core of the material science engineering is this triangle map here, where we investigate the processing, structure, and property correlationship here. And when I'm talking about structure, I'm talking about multiple scale. It's not just like from very micro scale, we're looking at grams, even from the atomic scale, arrangement of the atoms, point defects. I also see this as a structure. And all this will affect your properties. So have the data, you understand this database doing this. Eventually, I hope we can do a reverse design. So you know what the desired property you need. And then, based on the knowledge you learned from material science, you know what's the target structure. And then go back to the processing you need to choose to make this product. And nowadays, it's also very important to integrate computational material engineering here to help you understand what's happening during the processing. Instead of doing tons of experiments, you can simulate first. And here's what I'm going to cover today. It will be a very broad topics, including my previous research and some representative computational work I have been doing, and the current research I have been involved in future research. And then in the end, I'm also talking about my teaching experience and interest. So don't be surprised if I skip some slides there because I'm not going, the time doesn't allow me to go very in depth for each result. But I want you to get a sense about, what I have been doing to investigate that triangle correlationship here. So first, since 1990s, the idea of nanostructuring has been growing the world of science and technology. And some people talking about nano when they talk about nanoparticles. But what my research has been focused is bulk nanostructured materials. So from the outside, you still see a solid part. But if you look into the internal microstructures, especially for metals, the traditional materials give you kind of a limit of the grain size, about 10 microns. But now people are trying to modify the internal structures to bring in higher volume fraction of the grain boundaries. And those grain boundaries can give you some unique physical properties which cannot be achieved in traditional materials. So I just take the mechanical property as an example here. So this is the very early work, foundation about the nanostructure of pure copper. True stress and strain curves. The lower part curve is for traditional material which have a grain size in terms of 50 microns. But once you reduce the grain size into 25 nanometers, now you have a dramatic increase in the strength here. So you see the benefits we can get when you doing nanostructuring. And there has been very well established about the mechanism here, where the grain boundaries can help to stop the motion of the dislocations. So you need to apply higher stress to really deform the materials. And it's governed by a Hall patch relationship here, where the strength is in kind of reversely proportional to the grain size here. But in reality, most of the engineered materials are not pure metals. They are more complex. They can contain multiple components. So what I have been thinking is how can we extend or how can we use the benefits we got in nanostructure, apply them to real engineering materials. So I selected two very complex alloys from my previous research today as an example to give you an idea how nanostructuring can change their microstructure and their properties. So first we already talked about the question about what and why. Now we need to figure out how we can make those bulk nanostructured materials, right? So there are a very wide range of processing techniques to create nanostructure. One technique is called the severe plastic deformation. You can direct deform the bulk material, or you can start with powder, using powder metallurgy here. So the technique I have been using is called the cryogenic ball milling. So this schematic is showing one apparatus. This is a real apparatus, and here telling you during the milling, the powder will be milled inside a slurry made of milling balls and liquid cryogenic media, for example, liquid nitrogen here. And then the impeller will be rotating at a very high speed. So we take advantage of the collision between the balls, the impact, to deform the particles. And this showing you the three-stage, how the nanostructure is created. If you start with a relative coarse grain and you deform is during the impact between two balls, you will get a very high dislocation density within the grains. And as the milling time goes on, those dislocations will evolve. They will either annihilate each other or pile up and form those cells, and then transform to a more equilibrium boundaries. So now you convert the original coarse grain to a grain now have a couple grains inside. So you introduce grain boundaries into a particle. And the reason we are doing the powder, because if you have the powder, you can have the ability to scale up your research, because you can always make as much as powder you need. That's why I'm showing this equipment which allow you to make 1 kilogram of the powder at a time. And there are even higher scale up facilities which allow you to put in 5 kilograms at a time. And the previous work from my advisor group, they have been showing the cryomilling, this technique can generate narrow size particles. This is a TM, a transmission electron microscopy showing those grains here in terms of size of 20 nanometers. So within 12 hours, you can already generate a powder with such narrow sized. And what's more interesting is something we didn't expect at the very beginning, but we did turn out to find. Cryomilling also leads to some in-situ formation of narrow-scale oxides and nitrides, dispersoids in the powder. I hope the people in the back can also see here. This is a high resolution showing you the atom arrangements, and by measuring that distance between them, you can determine which compound or which material it is here. So these two unique features cryomilling giving an idea we can apply this method to a complex engineering materials also because we can start with the powder. So now I'm going to move into detail about the nitroid bond coat in thermal barrier coatings here. So thermal barrier coatings are very commonly used to protect gas turbine blades from a very harsh environment, very long thermal exposure at high temperature, usually about 1000 degrees C here. So people apply these multi-layer thermal barrier coatings, which include a ceramic layer here, which provides the thermal insulation, and a metallic bond coat in between to provide adherence between the substrate and then the top coat and reduce the thermal expansion mismatch here. And in between here, we also will find an oxide layer forming between the top coat and the bottom coat. So it's very important to be aware of this oxide is not like a layer we put it in purpose at the beginning. It's a reaction product during the operation of the thermal barrier coatings due to the diffusion of aluminum to this interface and then the oxygen penetration to this. Ideally, we hope this oxide layer will be a pure alumina because some will understand alumina is kind of a self-oxidation terminating material. So once you have a thin and homogeneous layer, it can prevent further oxidation into the substrate here. And we also wanted to grow like homogeneous to reduce the stress created during the formation of this oxide layer. And this oxidation behavior is controlled by this bond coat. Because your aluminum here comes from the bond coat there, and that's why I'm interested to see what the nanostructuring of this metallic bond coat can change the oxidation behavior. So one of my previous colleagues, he found out if we if we develop those thermal barrier coatings using the chromiold powder, we can get improved thermal cycle lifetime, which I highlight those bars. The black darker region bars are correspond to a chromiold material, and the light one are the conventional. But at that time, we don't know the mechanism yet. We just know, okay, we use those chromiold powder as the feedstock, and then we get better things. And that's like back to 2006, and that's when I came to US to pursue my PhD. So that's my focus of my PhD, to figure out what's the mechanism underneath here. So I end up first, I need to make a lot of materials using the cryogenic ball milling, and then we use a technique called the high velocity oscillophill to deposit those powder into coatings. And then we need to apply some post heat treatment to reduce the residual stress here. And this is the example about the coupons, including both the substrate and then the coating on the top. To investigate the mechanism, so I also made a lot of conventional materials using the identical processing lot without the chromiold. So using some gas atomized coarse grain powders as the feedstock to make this. So first I look at the powder we got, like to see what's the grain size we got after chromiold. So this is again the transmission electroscopy graph of the powder, and we see the grain size is around 25 to 70 nanometers when we also use some energy dispersive spectroscopy to identify the chemistry of some of the particles and find they are aluminum and yttrium-rich oxides and nitrides inside here. So it's very consistent to what we have been finding in other alloys making with the cryogenic. So we're using this nanostructure powder. Then now we want to see what's the microstructure look like when we spray them and then make the bond coat. So on the left, you are looking at those where I call it conventional, made from the gas atomized powder. So it has a coarser grain size, like 2 microns or above. And on the right, the chromiold one, we're using the nanostructure powder as the feedstock. So you already notice the distinct. You get like those continuous interpass oxidation between the in between the high velocity oxygen spraying, and that's a very well established phenomena people has been reported about. However, in the chromiold material, we don't see this anymore. We see still those very small, about like below 300 nanometers dispersoids were very well distributed in here. And if you recall the TEM results of the powder, I already showed those oxides and nitrides already exist in the powder. By doing the EDS mapping, again, we're trying to further identify the chemical composition of those. And we do find, in addition to the aluminum yttrium-rich oxide, we also find aluminum-rich nitride in this system. So now we wonder, since the thermal barrier coatings are used at high temperatures and for a long time thermal exposure, will those microstructures be stabilized after a long time thermal exposure? So I also studied the thermostability of this dispersoids. So I heat up the whole coating system at 1100 degrees C for different times. And you will see this, there is a little bit growth in terms of the dispersoids, but the distribution still stay as the same here. So it's very, I'm very confident to say those features, microstructure features are very thermally stable. So after understanding, the microstructure of the bond coat itself right now it's the time to see, okay, how this microstructure will contribute to the oxidation behavior. So now we kind of zoom out to really look at the three layer. If you recall, the whole thermal barrier system have the top coat, bond coat, and substrate. And this interface is where the oxide will form. And we would like the oxidation behavior to be more homogeneous, otherwise you might get stress and the top coat will spot off from the substrate. So this is as spread condition. And if we look at the interface here, we only get very limited oxidation at the interface. And now if we start to put the heat treatment now in air, like where the real operation environmental will be, I'm going to run very quickly several SEM images here, but when I'm doing that, I would like you to pay attention about this dark region here, about the thickness and some arrows I point, give you a different contrast. That might be a different, not might be from the EDS, we identify that's a secondary oxide phase instead of the alumina. So this is 1 hour, and after 4 hours, 8 hours, 10 hours, 50 hours, and 100 hours. So this gives you an idea about the thickness or the qualitatively distribution of this. But I do quantify, the oxidation behavior by really doing statistical measurements on the thickness of the TGO here. And the thing I didn't show here is the XRD and then the EDS mapping, which help me to understand what's the composition of the oxide layer. But coming back here, if we plot the thickness, the average thickness with arrow bars, which is the standard deviation, giving you the idea about how homogeneous the TGO layer is across the time here. And you will see the chromium give you the TGO growth in this chromium coatings achieve the steady state very quickly. And it's end up with a thinner oxide layer here. And you also will see larger values, which is the red arrow bars here. For the standard deviation for the chromium powder, it's smaller. So that means you get more homogeneous growth in terms of thickness. And then I look closer at the very starting point. So it's kind of a zoom out of a zoom in of the previous figure, very first 10 hours. So even though the chromium powder, the chromium coating start with a thicker TGO layer, I think that's due to we introduce a lot of grain boundaries into there, which provide a very faster diffusion path at the beginning, giving you this. But as the time goes by, actually it's very stable, and which give you the longer thermocycling lifetime for this. So then I kind of want to really develop mechanisms, how the microstructure gives you the final growth of the oxide layer here. So kind of schematically showing you the key features between the conventional bond coat and the narrow structure bond coat. And because of those dispersoids are rich in aluminum, which is the key elements for you to form the oxide. So I kind of modeling this by set up the boundary conditions and solve the diffusion equations. I'm not going to go detail about the mathematicals, but we came out with a solution, find out the diffusion rate of aluminum is proportional to those initial aluminum concentration at each I can divide the bond coat in very thin area, thin thickness to analyze this. So the mechanism come out, the aluminum outward diffusion is controlled by this homogeneous distribution of those aluminum-rich oxide and give you more constant aluminum concentration profile at each divided thickness here. And finally give you the uniform and homogeneous TGO thickness of the chromium coatings here. And also it's because the more homogeneity rate of the aluminum, our diffusion, you can avoid all those spinel, the second phase oxides here. It's kind of a recap, about what I have been, and the real my PhD work is more than this because I have been skipping a lot of microscope and then other characterization work here. But I just want to give you an idea about how how my research is involved in that triangle. We got, improved properties, which is good, but we don't end up there, right? We need to know why this. Can we reproduce the same thing, or can we use the knowledge we learned from here to other material systems? So it's kind of learning the microstructure of these different, two different coatings, and to really study about the composition of the oxide and how the microstructure of the bond contribute to this. So that's kind of wrap up of my PhD work here. And then I continue to work on aluminum 7000 series alloys, where it's usually used as a structural material for aircraft or transportation. And it's a project funded by Boeing. They want to really make light and strong materials. So they wanted to extend the idea about nanostructuring to this complex engineering material. This is a background about the application here. I'm showing you a kind of breakout of a Boeing 737 aircraft, showing you how much the pink and the dark gray area, how much of the airplanes are made of this series of alloys. And it's interesting, recently, actually Apple Watch, they also start to use this series of aluminum as the framework for this watch. You might wonder, why this special class of alloy attracts so much interest here. So this is, we call Ashby plot. I generated it using the CES software, which I used for teaching. Because we want light and strong, right? So the y-axis is the specific strength. So it's your yield strength divided by the density here. And environmental issue, it's a global issue now. People, care about green engineering. So the x-axis is the embodied energy. So it's kind of how much energy you need to consume to produce 1 kilogram of these alloys from traditional. So we want, the desired material should be towards this end. And guess what we find? All the aluminum 7000 series. So again, those smaller bubbles is point to those specific class of alloys. This big bubble is which represents the whole aluminum alloys. I mean, I use this software to generate more broader materials world, which also include the ceramics, but then it makes too messy to really identify where this it is. So now you might wonder, so why these alloys can give you highest specific strength, right? It's a very special class of alloy, which we usually call it heat treatable alloys. So upon the heat treatment, this is the hardness. The hardness of this alloy can increase upon treatment until it achieves a peak hardness. And if you continue to treat that, you will get softening. And in industry, they usually call this condition the T6 temper, where you get the highest hardness here. So what contributes to this special hardening response to the heat treatment? It's time again to look at microstructure inside this alloy. Reminding you this alloy contains magnesium, zinc, and copper in it. Those elements are not those perfect 100% in solid solution in aluminum alloys. So the material usually, you will heat it up at a high temperature and then quench it down at a very fast cooling rate. If you look at the phase diagram, that's the method where you can put more solid salutes in the matrix than the equilibrium state. After that, then you start to heat up the materials. Then the magnesium and zinc, they don't like the status because now the energy becomes higher. So they will creep it out, which we call the GP zones. And this is a very old paper, at the very beginning how they find out this, and it's from a commercial 7075. And as you continue to heat treat the materials, you will find some needle-like crystals, which is the beta prime magnesium zinc 2. And here I just provide a table kind of summarize what's the morphology like And more important, I would like to highlight the GP zones and the eta primes due to their morphology and the size are responsible for the strength we got in this alloy system. And if you continue to heat treat, like after the peak, if you continue to heat treat the material, which in English they call it the over-aged temper, they also sometimes use T7 to identify that. You will see the eta prime phase now transformed to like coarser, lot-like eta phase, which is still useful because there are some trade-off between the properties. Now you sacrifice your strength a little bit, but those equilibrium eta phase will give you more or higher stress corrosion resistance. This just giving you, some of you might have mechanical behavior background, give you an idea for the students why those preplates, those small dots, per your say how this contribute to the strength. So it's again, if you have those small preplates coming on, and then you have one dislocation line moving here, those preplates can again play as a stopping and impede the motion of this by forming those all around looping. And there is also a equation governing these mechanisms. And on the top right, it's where those preplates really look like and how they see forming those dislocation loopings, giving you an idea about this. And if you look at the equation here, the strength those preplates can contribute to the materials, it's dependent on the size of the preplates and then the interparticle spacing between them. So that's why the distribution of those preplates, how you manipulate those microstructures are important during processing, which can give you the desired property, either the higher strength or a higher stress corrosion resistance. So now it's time to combine the nanostructuring and the precipitation strengthening here. Because as nanostructured material right now actually have a wider definition now. Sometimes people can even call the commercial 70 to 75 material a nanostructured material because they have those nano size precipitates. But what I'm going to talk about right now is now we combine those grain boundaries with those precipitates and to see what we can get from there. There are some early work, who applied different methods, like they just directly deform the bulk material to reduce the grain size inside. And it's not surprising, you see the increase in strength compared to the traditional materials here. However, at that time, like the high pressure torsion method they use, they usually make like the sample in this size, and while the scale bar is 1 millimeter scale bar here. So we really want to extend the benefits to real material can scale up. And that's where my research, contributed to further this area. So having all those backgrounds set up here, and then what has been already learned for this system, the objective for my research on this area is to fabricate, those bulk nanostructure materials through the powder metallurgy, followed by consolidation, which give you the capability to scale up. And also, I'm really interested to investigate what's the mechanism here. What's going on here? Like, are we going to add up two strengthening mechanisms straight to get, like, if you get A from the grain boundary strengthening and you get a value of B, is the final strength will be A plus B? You will see that in the following here. And also to do that, I need to provide like more quantitative insights of the strengthening mechanism here. This is just material processing out. I'm not going to talk in details, like it's just followed with consolidation and secondary thermomechanical processing. But again, for each material, I made a coarse grain counterparts using identical processing without the cryogeny here. So this is what we get in terms of mechanical behavior. On the left, when I call it coarse grained, it's still in terms of like 2 or 3 microns because we still using powder metallurgy. And on the right-hand side, now I call it ultra-fine grain because after all those thermal exposure during the consolidation and then the secondary thermomechanical process, you got a little bit grain growth. So now we are not talking about grains on the order of 20 or 30 nanometers. We are talking about like a couple of 100, like 100 nanometers to 200 nanometers here. So first, the highest strength we can get is like 334 megapa compared to the Curve 5. It's a commercial 77.5 material. So this is where I just buy a material from the market and then test it. And more interestingly, I also find the T6 temper, like where you get an increase from Curve 1 to 4, is much larger than what we can get from the ultrafine grain material. We still get some strength increment from the precipitation behavior after T6, but it's not as large as I want it to be. So then it's now, again, the time where we need to understand what's going on here. Why I didn't get as much strengthening in terms of precipitation as I see in the traditional material. So that's where I first to look at the microstructure in the extruded condition and then after the T6. Just to remind you, T6 is the processing will bring you those precipitation strengthening here. So I'm going to skip a couple of TM images, but I don't want to let you kind of get a sense that those are really a lot of work to get those TM samples to bring in. But when I try to show, what we focus on is looking at the grain size, looking at the precipitates, looking at the dislocations. So each slide corresponds to different materials in different conditions here. But I do have a schematic which I would like to stop here to explain what happened, from what we observed from TEM. So on the top are the ultrafine grain material made from the chromium pot. On the bottom is the coarse grain materials. So because we have so high volume of grain boundaries, which is a very good thing for vacancies and dislocations during the thermomechanical processing, they kind of decrease the nucleation sites for the precipitates and hinder the homogeneous nucleation inside the grain. So that's why in the microstructure, which I skipped, but we do see very limited heterogeneous nucleation of precipitates at dislocations in that material. And because of the grain boundaries, we have segregation of magnesium and zinc to those grain boundaries. So we find some coarser zinc and copper intermetallics at those grain boundaries. And then after T6, although we still see precipitates, but the thermal exposure now anneal the dislocations more easily because of those high volume of grain boundaries. And then we get, compared to the traditional material, now we get not much heterogeneous nucleation sites for the precipitates. And that's why we see from TM only very limited number density of the precipitates. And this is just a comparison in the coarse grain. We can see a lot of dislocations in the microstructure, which assist the heterogeneous nucleation for large size eta prime phase. And we even see much coarser lace-like eta phase. Again, this is in the as extruded condition, so we haven't applied T6 temper yet to this. And after the T6 temper, although we also have some annihilation of dislocations, but because now the grain boundaries are far away from each other, there's still room for you to maintain the dislocation.